Hello. In this video, I'm going to talk about the definition of the limit. Now, we have that the definition of the limit before said that as long as the limit from the left is equal to L and as long as the limit from the right is equal to L. Okay, so that kind of makes sense in some cases because, yeah, if you have that you approach it from the left and the right arbitrarily close, then or sufficiently close, then yeah, it's going to be what you expect it to be. However, there is a definition that we go by that's more precise. So we say that for uh, every epsilon greater than 0, there exists a delta greater than 0 such that, okay, so here we just say that the function value, or the function itself, minus the limit value cannot be less than, or it's less than epsilon whenever, okay, so we have that that's whenever you have that the distance x minus, in this case, a, is less than delta. Okay, so that's quite a bit to take in if you think about it. One way of which that we can kind of say is that essentially all that we're saying is that delta is more or less, or epsilon is more or less like a bound. So like if you know that your limit is L, maybe you don't want it to be any further away than 0.01 units, or maybe like 1 unit, but 1 would be too much. So usually we stick to no more than no more than 1 unit respectively. So let's try to digest this, because it's a lot better to see it with a real number or something like that. So like let's say like you have the limit as x approaches, um, let's say just 2 for 2x. um, so let's say that we have 2x plus 4. Now we know that this limit is equal to 8. But let's suppose that we go ahead and we set the epsilon equal to 0.01. Okay, well, if the epsilon is equal to 0.01, that means that we can find our delta that corresponds to this. So in either case, what's happening is that we're kind of like creating a window that defines like a range, and that range corresponds to a specific window that would correspond to the domain. So essentially, we're kind of like surrounding 2, and we're trying to find out what's the delta that's to the left and to the right of 2. So we look at this and we put that we have our function minus 8 is less than 0.01. So what this does is it tells us that we have negative 0.01 is less than f of x, which is minus 8, which is less than 0.01. Okay, so that's not too bad. Next, we just go ahead and we add 8 to both sides. So we have 8 minus 0.01 less than f of x, and that's less than 8.01. Okay, so the next thing to do would be to put, let's say like 7.99 is less than, well, what is f of x? F of x is actually just 2x plus 4, and this is less than, let's see, this is less than 801. Okay. Now, the next step would be to basically just get x by itself, because you want to know like what that delta happens to be. So we do some more algebra. We subtract 4 from both sides, and we get, let's see, that'll be 3.99 is less than 2x, and this is less than, okay, so that'll be 4.01. Okay, so now we're going to go ahead and we're going to actually solve for x. We're going to divide by 2 and divide by 2 and divide by 2. So what we get here is the following: 1.995 less than x, and that's less than, let's see, that's less than 1 point, actually it's not 1 point, but it's 2.0. Okay, so let's just do this again. 2.005. Okay, now notice that basically we kind of have our delta, because look at it this way. We know that a is equal to 2. Okay, so in that case, that would mean that essentially we know what the largest delta is. The largest delta, if you want to do like 2.005 minus 2, that means that the delta is equal to 0.005, which basically means that essentially we just want delta to lie between 0.0005, no bigger than 0.005, but greater than 0. So that would be it. We have that the delta that works is 0.005. And if it helps, like think about, like, for example, like how close you're getting. Just think of it this way, that you're looking at an interval 1.995 comma 2.005, which means that this open interval is the one that corresponds to that we're within zero point zero 0.01 of our limit value. So in this case 7.99, and then we have 8.01. But notice that if you plug in 2.05, you will get 4.01, and then you'll have plus 4 um, is going to be the 8.001 or 8.01. So that's kind of the idea, but if you want to think about it in terms of like what does that look like in the x and y plane respectively, so like just in general, not, let's just write it in general because it'll be kind of hard to draw. Let's see, okay, so like say for example that you have a linear function, but suppose that there's like a little small piece that's missing. Not like that, but we'll just do this and just do that. So this value is our c. So we have to pick a value over here that we call c plus delta. Then we have to pick a value over here that we call c minus delta. So basically there is kind of like a correspondence as it relates to what these values will be equal to along the graph. So right here, this is f of x plus epsilon, and right here, right about there, that's the f of x minus the epsilon. And then right here, that's the f of x. Actually, these should be L plus epsilons and minus epsilon. So like, let me get rid of that. Okay, so that should be L minus epsilon and L plus epsilon. Now, if this was more like a nonlinear function, then, because notice that there's kind of like symmetry about here. So we have that, it doesn't really matter which delta we choose. But for instance, if you were to choose, like for a nonlinear function, a delta, then you would want to make sure that, for instance, that it contains, well, that it's close enough to the constant, because like if you have something like this and this is your limit value, and then you say that you want it to be within epsilon, so notice that over here, like if this is L plus epsilon, this is going to be C plus delta, but this is too far away. And then if you choose L minus epsilon, well, in this case, you have that this is closer. So you have C minus delta. So this one right here, this one's actually closer than this one. So if I was looking for a delta, I would choose this one over here as opposed to this one over here, because I'm too far away from my constant C. So it's kind of like the same idea like with tangents, that you want to be as close as possible. Okay, so let's say, for example, that we try to show, um, let's say that we try to show a similar, where we want to find the largest delta that works. Okay, so we want to find the largest delta that works. And for this one, we're just going to say that we have the limit as x approaches 4 for 2x equals to 8. And for this one, we're going to just choose 0.1. Okay, so that's going to be our epsilon. So this is more or less like a glorified college algebra problem, because essentially we're just trying to see like how close can we get to 8.1. So this is actually kind of similar to the one that we just did. The only difference is the numbers, obviously. So we have that this is going to be 2x minus 8 is less than 0.1. And then from here, one way that we could do this really interestingly is like take out the 2, multiply by, so yeah, take out the 2 and you have x minus 4, and that's going to be less than 0.01. But notice this, that you end up with x minus 4 is less than 0.01 divided by, it's not 0.01, is it? Yeah, it's 0.1. So then that means that this over here has to be 0.1. Yeah, sorry about that. So, okay, so we have that that's going to be 0.1. Now, notice that if I divide by 2 on both sides, basically I kind of already found my delta, because this equals to 0.05, and that means that this is going to be equal to delta, because notice that this is x minus 4 and that's less than delta. Okay, so because yeah, remember that in the definition, basically it says that for any epsilon greater than 0, we have that there exists a delta greater than 0, such that you have that the function minus the limit value has to be less than epsilon whenever you have that the 0 is less than the x minus the 4, and that's less than the delta. So the fact that this looks just like that is actually no coincidence. So in this case, we'll just say choose delta to equal to 0.05, and that's it. Okay, so let's say that we look at another one, and suppose that for this one, okay, so yeah, what I want to do is basically just look at showing when a limit is equal to, well, yeah, we're just going to prove a limit. Okay, so most of the time it says something like show that the limit is like let's say like as the limit as x approaches 3 for 3x plus 7 is equal to 16. Now, most students will just say, well, isn't 3 times 3 plus 7 equal to 16? And the answer is yes, but that doesn't really show much because, you're still not necessarily proving it. So here, I'm going to just use a little bit of scratch work. And that scratch work is going to be where I have that f of x minus 16 is less than epsilon. I know that much from the definition. So this is 3x plus 7 minus 16 is less than epsilon. But if I move on even further, I have 3x minus 9 is less than epsilon. So from here, we have that all that we need to do is factor out the 3. So I have that 3 multiplied by the absolute value of x minus 3 is less than epsilon. So here I just divide by 3 on both sides. So once I do that, I end up getting that the x minus the 3 is less than epsilon over 3. But that means that delta is equal to epsilon over 3. So in that case, I found a delta that works. So whenever you do this, you start with the proof of it. So you'll just say that for any epsilon greater than 0, choose delta to equal to epsilon over 3. So from here, you would say that okay, so we have that f of x minus 16 is equal to, okay, so this is where it gets kind of weird. It's like 3x plus 7 minus 16, and that's going to be equal to 3 times x minus, let me see, 3 times x minus, let's see, 3, which that's going to be less than 3 times delta, which is equal to 3 times delta over, well, 3 times delta is actually, right, so that's actually epsilon over 3. Okay, so that's going to be epsilon over 3, but that's going to equal to 3. Not 3, they both look alike. So that's going to equal to epsilon. So this gives us basically that the limit exists. So we have that the limit as x approaches 3 for 3x plus 7 equals to 16 whenever you have that the x minus 3 is less than delta. One of the variations of the proof is usually that, you could actually just say let epsilon be greater than 0, choose delta to equal epsilon over 3. What this means is that you have that f of x minus 16. So basically you'd just be repeating the same thing where you end up with that 3 times x minus 3 is less than 3 delta, which is 3 times epsilon over 3, and then that equals to epsilon. And that would be if, for example, so like if you have this, then that means that that gives you You could say something like that, like thus the limit exists, um, if you rather do it this way. But another thing that you would have to put in here somewhere is that you would have to assume that x minus 3 is less than delta but greater than 0 in order to, fully prove that that is what you expect. Now, most of the time, like I say, if ever you have like some trouble like trying to figure out the definition of the limit, it always helps to kind of just draw it out, because once you draw it out, then you can kind of see like where you're supposed to go from there. Because like if you have 3x plus 7, okay, so in that sense you have 7, uh, and then maybe like right about there is your 16. So like if this is 3, then essentially you know that you want to find a largest epsilon, or largest delta. So that'll be 3 plus delta. And then maybe like over here you have 3 minus delta. Okay, so in either case, like just be sure that you kind of have an idea on like how the picture kind of looks. And then of course, um, you would have to find your 16 plus epsilon, and then you would have to find your 16 minus epsilon, and then from there just kind of work out the definition. Okay, so now what you should definitely look at, for example, is like for instance, try looking at the limit as x approaches 2 for x squared equals to 4, but do it in a way where you use that epsilon is equal to 0.01. Now that's going to be pretty tough in terms of like figuring out like what delta will be appropriate necessarily. So this is going to be an approximation. Um, so yeah, basically you're looking for what delta is equal to. Another that you should definitely try is to show that the limit as x approaches 2 for 1 over x is equal to 1 half. Now, interestingly enough, like if you do try these problems, you'll have like a better understanding of the epsilon and deltas, like how does it work, like in terms of like giving you the limit itself, or the limit. But note that like, you should really think about other types of things, like for example, like how do I know that the limit of a constant is equal to the constant b? How do I know that the limit as x approaches a for x is going to be equal to a? Like try to think of these, like, does it matter really like how far or how close we are to a? And then think about like what delta would work for the constant, the identity function, sorry. Um, but then note that, for example, that it gets more complicated for things like, like if you're taking the limit as x approaches a of x squared, and you know that that's equal to a squared, then that really does, that does actually get a little messy in terms of like, you know, what is the largest delta that works for that one, and especially like square root functions, like yeah, like square root of x or any variation of that, because essentially the delta is going to be an approximation. It may not be an exact value. So that's one thing to consider, but normally after we do this section and students are like thinking, well, do I need to show that for polynomials? And the answer is no. Because yeah, once you start looking at nonlinear functions, it becomes more complicated. So really, you're only asked to look at, things like the the linear functions, and then also these examples of finding the deltas. I'm giving you this one, 1 over x, just so that you can kind of see if you can do it, because it's actually not that bad. you'll realize that what the delta or epsilon that works for this one would be. Okay, and that's going to be it.